Good evening, scholars. Mr. Spears here. Mole problems got you down? Well, in today's lesson, I'm going to show you how to get your mole problems under control. We've seen this picture before in some previous lessons, and what I want the student to take from this diagram is how the mole is central to this unit. Whether you're going from mass particles or from particles to volume, mole is the bridge that connects the two. But in order to make those calculations, we've got to remember three very important relationships. First, let's start with Avogadro's number. As you're reading these word problems, if you see anything that has to do with a represented particle, whether it be an atom or an ion or a formula unit, these are a dead giveaway that you are going to have to use Avogadro's number and this relationship that Avogadro's number is equal to 1 mole in your problem. Next, 22.4 liters is the volume of 1 mole of gas at STP. If you get a problem and it asks for the volume or something with liters at STP, that is a telltale sign that you're going to have to use 22.4 liters is equal to 1 mole somewhere in your math problem. And finally, molar mass. Anything that has to do with mass or grams, you know that you're going to have to use the relationship molar mass equals 1 mole somewhere in your problem to help solve it. In the next 4 slides, I'm going to work through 4 example problems. And these 4 problems are not advanced because they're particularly difficult, but just simply because they require more steps than what you saw in a previous video. So in our first example, we are asked how many formula units are in 140.34 grams chromium-3 sulfide. So I'm going to start by making a picket fence, put my given in the upper left quadrant. Because I want to get rid of grams of chromium-3 sulfide, we'll put that unit down below in the next fraction. Now, like I said, anytime you see grams or mass in your problem, I want you to think of molar mass. So to get where we need to, we're going to have to find the molar mass of chromium-3 sulfide. Quick molar mass calculation gives us 200.2 grams per mole as the molar mass chromium-3 sulfide. Now, before I can get to formula units, I've got to change these grams into moles using molar mass. So I'm going to put the molar mass in grams down below with the grams, and then this is equal to 1 mole of chromium-3 sulfide. Grams cancel out, and I'm left with moles of chromium-3 sulfide. This is not what I'm asked to find. I'm asked to find formula unit. Anytime I see formula units, which is a type of represented particle, I know that I'm going to have to use Avogadro's number somewhere in this problem. So to get rid of those moles, I'm going to extend my picket fence. I'll put moles of chromium-3 sulfide down below because I'm trying to get rid of it, and put formula units of chromium-3 sulfide up top because that's what I'm trying to find. I know that 1 mole of chromium-3 sulfide is equal to 6.02 times 10 to the 23rd, and now this cancels out my moles of chromium-3 sulfide. You'll notice that the only unit standing is formula units, and that's what I want. So now I'll multiply by every numerator and divide by every denominator. So I want to show you how to enter this into your calculator just simply because we're dealing with numbers written in scientific notation. 140.34 times 1 times 6.02 E23 divided by 200.2 divided by 1. Hit enter, and we get our answer rounded to the appropriate number of significant digits as 4.2200 times 10 to the 23rd formula units of chromium-3 sulfide. In our next example, we are asked to find the volume in liters of 9.4 times 10 to the 22 oxygen molecules at STP. Right off the bat, I see some key indicators of relationships that I'll be using in this problem. Liters, volume, and STP, these all indicate that I will use 22.4 liters is equal to 1 mole somewhere in this problem. Also, I noticed that molecules, a type of represented particle, is in this problem, and that's an indication that I'll use Avogadro's number to help solve this problem. So I begin by writing a picket fence. Start with my given 9.24 times 10 to the 22 oxygen molecules. I'm going to put oxygen molecules down below to cancel it out in the next fraction. And because I know that I need to go to moles before I go to liters, I'm going to put moles of oxygen up top. Now the numerator and the denominator in this fraction need to be the same amount. So I know that Avogadro's number of particles is equal to 1 mole of that substance. Oxygen molecules now cancel out, and I'm left with moles of oxygen. I don't want to find moles of oxygen, I want to find liters of oxygen. So I'm going to extend the picket fence. I'll put moles of oxygen down below, liters of oxygen up top. To get the numerator to be the same amount as the denominator, I remember that at STP, 1 mole of any gas has a volume of 22.4 liters. Moles of oxygen now cancel out, and I'm left with liters of oxygen. That's what I want to find. So all I need to do is multiply by my numerators and divide divide by every denominator. When punched into the calculator and rounded correctly, you get 3.44 liters of oxygen as your final answer. In our third example, we were asked to find the mass in milligrams of 0.52 moles of sodium hydroxide. A couple things should jump out at you. The words mass and grams, these are indicators that molar mass will be used in this problem. But we also noticed that the metric prefix milli is attached to grams. Because molar mass is in grams and not milligrams, we know that in order to solve this problem, we're going to have to perform a metric conversion. So start by drawing a picket fence, but you're given up top 0.052 moles of sodium hydroxide. Put moles of sodium hydroxide down below so that they cancel out. And to get from moles to grams, we've got to use our molar mass relationship. So I'm going to put grams of sodium hydroxide up top. So I know that 1 mole of sodium hydroxide is equal to the molar mass of sodium hydroxide. And a quick molar mass calculation tells us that the mass of 1 mole of sodium hydroxide is 40.00 grams. Moles of sodium hydroxide cancel out, and we're left with grams of sodium hydroxide. Now this is not milligrams, so we're going to extend our picket fence and do one more conversion. I'll put grams of sodium hydroxide down below and put milligrams of sodium hydroxide up top. To get the numerator to be the same amount as the denominator, I know that for every 1 gram there's 1,000 milligrams, because that's what the prefix milli means. Alright, grams of sodium hydroxide cancel out, and I'm left with milligrams of sodium hydroxide, and that's what I want to find. I'm going to multiply by every numerator, divide by every denominator, and when I punch the values into my calculator and I round to the appropriate number of significant digits, I get 2,100 milligrams of sodium hydroxide. In our final example, we are asked to find how many chlorine atoms are in 0.73 moles of phosphorus pentachloride. Now the word atom should jump out at you as telling us that we're going to use Avogadro's number somewhere in this math problem. But notice we're given phosphorus pentachloride, but we're asked to find something out about just chlorine. Whenever you're given is not the same substance as what you're trying to find, you know that you're going to perform a mole ratio. So to get started, let's draw our picket fence, put our given in the upper left quadrant, 0.73 moles of phosphorus pentachloride. I'm going to put moles of phosphorus pentachloride down below so that they cancel out. And now before I can get to atoms of chlorine, I've got to first go to moles of chlorine. So now you'll see we have moles of one thing on top of moles of the other. This is a classic mole ratio. You'll see this a lot when we start talking about stoichiometry. The way you fill this out is to understand that the subscripts in a chemical formula give you the ratio of atoms in that compound. And so if I have 1 mole of phosphorus pentachloride, it's the same as having 5 moles of chlorine, because there are 5 chlorine atoms in 1 phosphorus pentachloride molecule. So moles of phosphorus pentachloride cancel out, and I'm left with moles of chlorine. However, this is not atoms of chlorine, so I extend my picket fence, put moles of chlorine down below, and chlorine atoms up top. I know the relationship between moles and atoms, or any type of representative particle, is that 1 mole is equal to Avogadro's number. With the moles diagonal of one another, they cancel out, and I'm left with chlorine atoms as my answer. And that's what I want. So all I got to do is multiply by every numerator and divide by every denominator. And when punched into my calculator correctly and rounded to the appropriate number of significant digits, I get 2.2 times 10 to the 24 chlorine atoms. Alright scholars, that concludes tonight's lesson. For internet viewers, if you have any questions, just hit me up at my YouTube channel. And for my students, write down any questions you may have to share in class. Thank you for watching and have a great day.